Okay, so we've got another lightning talk on the PICTOR telescope, a free-to-use and open-source radio telescope.
Okay, thank you very much. Hello everyone, my name is Apostolos. In this lightning talk I will present to you PICTOR, which is a free-to-use and open-source radio telescope that allows anyone from all around the world to observe the radio sky for free. Let's start with a little introduction. So this is our galaxy. I think most of you have already seen this image, maybe. But how did we take this image? Well, of course, we didn't send a spaceship there. That's a bit too far. But so how did we compose it? Well, we synthesized it. This is an artist's conception, mostly using radio astronomy. So you know, if you've seen the galaxy at night, the Milky Way band, you may not really be able to tell if we even live in a spiral galaxy. So today we'll try to prove this to you with a live observation. So let's start with the electromagnetic spectrum. I think you've all seen this sketch. So in the middle part we have the visible spectrum. This is a spectrum that we see with our own eyes. This is where most astronomy takes place in. And of course we have some invisible wavelengths like X-rays, gamma rays, infrared, ultraviolet, microwaves, and of course radio, which I will focus on today. So now under certain conditions, a neutral hydrogen atom can emit radiation, a photon with a wavelength of 21 centimeters. This is called the spin flip transition, which is responsible for the production of these waves. And as you know, our galaxy is full of hydrogen. So we can detect these spiral arms. You see, this is an all-sky map, and in the center we have the Milky Way, hence why it's so bright at 420 megahertz. This corresponds to a wavelength of 21 centimeters. So we wanted to build a radio telescope that can detect this very, very faint radiation and make it available to everyone to use online for free, without any registration, advertisements, or anything like that. So we began with some simulations for the antenna. This is a feed-horn simulation using electromagnetic solvers. This is the simulated radiation pattern. And after that, we decided to build the antenna and got it measured in the lab. This is the telecommunication systems laboratory of the Department of Digital Systems at the University of Piraeus. We got the graphs and everything. This is S11 of the monopole for those familiar with RF systems. And of course, we measured the entire feed horn, which made the monopole a bit more wideband. So let's look at some stats. It's a parabolic antenna with a diameter of 1.5 meters, so it's a large dish. It can operate from 1300 to 1700 megahertz. So if anyone doesn't want to observe the hydrogen line, he can look at a different frequency. The half-power beam width, this is like the field of view. It's about 9 degrees. And most importantly, it's got a filtered LNA, very low noise amplifier with a 0.5 dB noise figure. And of course, it's fully open source. So anyone can take the code and build his own. So this is what the telescope looks like in its current form. And this is basically the data acquisition flow graph, the digital signal processing. It's based on polyphase filter bank spectrometer. This is GNU Radio. Many of you know this. And you can find the full documentation here. I've made a separate documentation just for this flow graph. So how does it work? The signal enters the feed horn, gets amplified, filtered, and then amplified. This is a two-stage low-noise amplifier, and runs through a 3-meter low-loss coaxial cable. Then runs through a Faraday cage to reduce spurious emissions to the telescope, which is undesired. Runs through a bias T, an SDR, and of course a Raspberry Pi. So why don't we make an observation? So to make an observation, a user simply goes to pictortelescope.com, and you can scroll down. I've got the GitHub here and everything. Check some information out. And I've also written a PDF in English. You can take a look at that. It has some introductory radio astronomy information. So maybe that's something you're interested in for beginner users, for example. So we have here a form. It tells you where the telescope is pointing to. Right now it's in zenith, so directly overhead. So it allows us to, for example, put an observation name like like FOSDEM example. Center frequency, we want to observe the hydrogen line, so 1420 megahertz sounds reasonable. Bandwidth, you can go up to 3.2 megahertz, but 2.4 is usually sufficient. Then we have the number of channels. This is the FFT size. 2048 is usually fine. It's more than enough. And you have the number of bins, which basically determines the integration time per FFT sample. This won't really affect your signal-to-noise ratio. It's usually for interference mitigation and other kinds of things. So duration, let's just put 20 seconds and input our email address. So if we hit, oops, okay, let's run this again. So we said FOSDEM. Okay, 20-second duration and our email address. Okay. Right, let's hit enter. Okay. So now the observation is running, and the telescope just picks up this this observation. Let's actually look into this in more detail. So what happens is the user loads the observation page, the server checks if there is an observation running, and if not, it permits the user to submit an observation with his desired parameters. So then the telescope awaits the observation request, checks if it has already been run, and if not, then it runs the observation, does some digital signal processing, including RFI mitigation, etc., and then sends the data to the observer via email. So the user can just go into his email and check the observation data. So I think we should have received the observation now. Let's give it a second. It usually takes maybe a minute or two for the email to arrive. Okay, there we go. So we have here the observation parameters that we entered, bandwidth, sample rate, number of channels, and everything. And over here we have the graphs, so the telescope data. So we have 4 graphs in total. This is the average spectrum, this is the calibrated spectrum. So this is what the SDR receives, and you can see a very faint peak there, but you also see 3 humps. So this is called the bandpass shape, and it's due to it's like an SDR artifact. So if we calibrate that, it becomes flat, and we can see the hydrogen line a lot more clearer. So what we see here in this peak, this is the hydrogen line. This corresponds to a unique spiral arm in our galaxy. Specifically, this is the Cygnus arm, so our host spiral arm of a solar system. And we have 2 more graphs. The waterfall, which basically shows you the entire data. It's just not very easy to see, hence why you have some more graphs. And of course, power versus time. Okay, so if we go back to the presentation. Okay, so this is another example observation taken at an even better time. You can see three peaks here. So each of those peaks corresponds to a different spiral arm in our galaxy. So with just an observation, you can get such data in like 60 seconds, for example. You have detected 3 unique spiral arms of the galaxy. So you've proven that the Milky Way is indeed, like we do indeed live in a spiral galaxy, which is not very easy to prove using optical measurements. So let's look at some statistics. So PICTOR has been used from 360 plus unique users from all around the world. We have 2.3 thousand observations from the archive. Imagine our goal was to hit 100 unique users in a year, and in less than a year, in just a few months, we reached so many users, which is great. And these users include students, teachers, educators, professors, amateurs, and even professional astronomers. So, some future plans. We have a lot of plans for the future regarding radio astronomy. One of them is the development of a similar educational instrument for pulsar education, and maybe be part of research as part of the pulsar monitoring network, which will be dedicated for glitch research. Pulsar glitch is basically an open issue in an open problem in science, because what it means is a pulsar is a neutron star. It presents a sudden decrease, a sudden change in the spin period. So we're looking to research more into that. And of course, we have LyraNet, which will be a global network of open source radio telescopes. This include some small and large dishes. The largest one right now is 18 meters in diameter, so it's a huge dish. And we have some many more. And this network will be for research and education as well. So we have plenty of plans for that. And last but not least, we'd like to thank LibreSpace Foundation for their support and the support with the stickers, and also helping us build another antenna that will also be part of LyraNet. So yeah, thank you very much. And of course, feel free to take any stickers you want from over there, and I'll be happy to take some questions.
What's the cost of designing a telescope?
Okay, so the question is, what's the cost of designing such telescope? Yes, so it depends on the diameter, of course, and what backend you will use and what RF frontend. So maybe you want to go with some even lower noise amplifiers, some better filters, a larger dish, maybe you want to make it more wideband. So there's a lot of options. You can design a telescope like PICTOR for, a few $100, maybe less. We just designed a new one called Nano-RT, Nano Radio Telescope, which looks like an optical telescope. It's very small. This costed under 100. So there's a lot of possibilities, and if anyone wants to build a radio telescope, they can really do this. I mean, I've written all the software for you, so you don't have to go through this work as well. Any more questions? Yes?
Can you specify the sky location, like the coordinates, sky coordinates?
So the telescope basically points constantly to zenith. So you can use, students can use something like a planetarium, a virtual planetarium software like Stellarium to see where the telescope is pointing to. So the elevation sometimes changes. For example, on request, if a student wishes to observe the moon or the sun, for example, then they tell us, can you please shift it to a certain elevation? And they often perform drift scan observation. So they don't have, in the case of the moon and the sun, you don't have to observe at 1420 megahertz because you're not looking to observe the hydrogen line. You're looking to observe something much closer. So in the case of a sun or lunar drift scan observation, what you're looking for is the power versus time. In this case, you should see the power being mostly flat and slowly rising, forming a Gaussian curve, and then going straight like so. You basically see a peak when the sun or moon enters your field of view, the beam of the telescope. Any more questions?
Okay, thank you very much.
Thank you.